Quantum field theory is the most experimentally successful framework in the history of physics, yet its mathematical architecture relies on manual inputs. The standard model Lagrangian requires 26 free parameters to function. These constants include fractional charges, mixing angles, and a massive hierarchy of Yukawa couplings. The theory provides no underlying mechanism to explain their values. They are measured experimentally and inserted into the equations. Even the internal symmetries of the standard model are postulated. The gauge groups are an observational input, chosen because they fit the data, rather than derived from a deeper physical cause. The time force hypothesis offers a strict departure from this methodology. It replaces the paradigm of independent particle fields and canonical operator postulates with a single underlying geometry. The framework is built on a single, continuous, universal scalar field, denoted as phi, defined across 4 spacetime dimensions and 1 confined transverse coordinate, w. The observable universe, including the entire fragmented particle zoo of the standard model, emerges directly from the geometric and topological dynamics of this singular field. By treating particles as solutions to a single nonlinear equation, the time force hypothesis replaces algebraic inputs with deterministic geometric consequences. To understand how discrete particles arise from a continuous field, we look at the w-axis. In this model, w acts as the transverse structure of a universal wave face. This axis is subject to strict directly boundary constraints at plus and minus sigma 0. These geometric limits are fixed by the cosmological expansion rate. Inside these boundaries, the field dynamics are governed by a nonlinear eigenvalue equation, balancing kinetic propagation with self-interaction. The transverse confinement forces the continuous field to organize into a discrete spectrum of standing waves. Only specific resonant frequencies survive the boundary conditions. The lowest non-trivial mode of these standing waves corresponds precisely to the first root of the Bessel function, J01. Calculating the energy of this specific geometric mode yields a parameter-free prediction for a universal scalar mass gap at exactly 2.05 GeV. Quantization does not require postulated commutators in this framework. The discrete energy spectrum is a direct product of the boundary geometry. This 2.05 GeV confinement scalar establishes the baseline. It provides the architectural anchor for all subsequent mass structures. Examining a localized section of the phi wave face reveals configurations where the field twists and collapses into stable topological defects. In this model, fermions, like electrons and quarks, are these exact topological vortex defects in the substrate. Circulation around the defect's core produces a phase shift, dictated by an integer twist number, nq. This sets a geometric rule for electric charge. Q equals nq times elementary charge over 3. -3 maps to the electron. +2 matches the up quark. Beyond the phase winding, the core of the vortex houses an internal 3-dimensional orientation vector within the moduli space. A stable vortex admits exactly 3 orthogonal orientation states within the local wave face. Infinitesimal reorientations among these 3 geometric states generate an internal transformation matrix. This behavior produces the fundamental representation of emergent SU3 color charge. The specific fractional charges and color triplets observed in experiment are the direct physical manifestations of these vortex-core geometries. If we reject the use of arbitrary Yukawa couplings, the model must generate the vast disparities of the fermion mass hierarchy from geometry alone. This is achieved through zeta quantization. In this arithmetic structure, fermion masses correspond strictly to discrete equilibrium lengths, denoted as lambda n, within the universal field. This data table compares the observed standard model masses for all 12 charged fermions against the theoretical predictions generated by the time force hypothesis. The framework requires a single calibration point. The measured electron mass fixes the effective Planck factor, establishing a baseline. The remaining 11 charged fermion masses are then calculated using fixed arithmetic ratios from their zeta levels, maintaining a mean theoretical deviation of just 0.76%. Furthermore, the 3 generation families of the standard model align with the integer ordering of these distinct zeta levels. A single geometric arithmetic scale accounts for the entire fermion hierarchy, removing dozens of manually inserted mass parameters from the underlying physics. In a dynamic system, multiple topological vortices move, interact, and simultaneously alter their internal states as they navigate the wave phase. Their parameters of orientation and internal phase shift continuously. This equation for the effective action maps the evolution of those internal parameters over time and space, governed by the metric of the moduli space. The curvature and geometric inertia of these shifting internal parameters act as disturbances. As vortices adjust, they create secondary waves rippling through the surrounding phi field. We physically measure these secondary geometric ripples as gauge bosons, photons, gluons, and the W and Z bosons. The specific metric of this moduli space mathematically yields the Yang-Mills structure constants required to describe these interactions. The three spatial orientations of the vortex-core correspond to the SU3 color triplet, while phase rotations between internal modes reproduce the electroweak SU2 and U1 structures. Ultimately, these gauge bosons represent the geometric wake left behind as shifting topological defects navigate across the universal wave phase. The deterministic geometric behavior of the continuous field bridges the gap to the probabilistic reality observed in laboratory experiments. When observers interact with coarse-grained averages of the field, the macroscopic view of interacting vortices and moduli waves resolves into standard probabilistic scattering. Quantum field theory operates as a highly successful, low-energy effective limit of this deeper nonlinear geometric substrate. The time-force hypothesis produces sharp, falsifiable predictions that deviate distinctly from the standard model. The framework mandates a 2.05 GeV scalar gap resonance, detectable via rare meson decays. It dictates an essentially zero invisible width for the Higgs boson, driven by a 10 to the negative 43 geometric overlap, and it anticipates universal atomic scale phase drifts, measurable via interferometry from wave phase relaxation. To transition to a fully realized theory, final mathematical tasks center on rigorous spin statistics proofs and formalizing anomaly cancellations directly from vortex topology. By removing the arbitrary parameters and manual inputs of the standard model, the time-force hypothesis rebuilds particle physics entirely on a foundation of pure geometry.